Well, I am pleased to welcome Chris Fuchs, who is professor at the University of Massachusetts in Boston, and who is going to speak about what? QBism? Is it that? Of course, QBism. Well, next. So, the chair is yours.
Thank you. Thank you for the invitation. I don't always speak about QBism. There was a talk in 2019 that was not about QBism, but for the previous 10 years to that, and then up to 2019. It's always been QBism, which of course evokes the vision of Cubist art. So I used this photo, this painting, the nude descending a staircase number 2 by Duchamp, not because it's Cubist, but because I found this quote about it. Before its first presentation at the 1912 Salon des Indépendants in Paris, it was rejected by the Cubists as being too futurist. I suspect that might be true of some people who call themselves Cubists for what I'm about to say today, David Merman being one example of that. But with Michel Bitball and Laura de la Tremblay in the audience, I have a feeling they might think that it's not futurist enough. So what is Cubism? It's another damned interpretation. Everyone knows about this. Well, that comes from something that David Merman pointed out. Quantum mechanics is the most useful and powerful theory physicists have ever devised. Yet today, nearly 90 years after its formulation, disagreement about the meaning of the theory is stronger than ever. New interpretations appear every year. None ever disappear, David said. Wow, you can see what he was talking about. So here's a partial list of interpretations. These Copenhagen interpretations, you notice that there is an S because they're not all, if you read these fellows carefully enough, you'll find that they didn't all have the same views. Non-local hidden variables, there's Hervé's convivial solipsism, and the list goes on and on. We have Ravelli down here somewhere. And then at the very bottom, I don't know if you can see it from where you're standing, many worlds as promoted by Everett Hawking and science fiction fans all around the world. In English, and I presume in French, we have a notion of a collective noun. One can speak of a pack of dogs, or a herd of cows, a gaggle of geese. Are there any good French examples of collective nouns like this? When you speak of many crows or many snakes, is there a word for a family of snakes? Like here, a slither of snakes.
A bunch of philosophers.
A bunch of philosophers. Well, in 2017, I was giving a set of lectures at one of the Enrico Fermi summer schools, and I held a contest for the students to. The award was having a beer with me for the person who invented the very best collective noun for all of these interpretations that we just saw. And the winner was a bullshit of interpretations. But you know, this is serious work. Here I've got the same list, but I've highlighted in blue all of the Nobel Prize winners that have been thinking about quantum foundations. And if you think that it's not serious work, then you should question the Nobel Prize of these men. They've always been doing, and women, they've always been doing very serious work, and they saw this as part of the story of serious work. But students are told something different very often. They're told to shut up and calculate because you don't want to go in these directions. If you do, it'll destroy your career. I would guess this audience, everybody knows who invented the term shut up and calculate.
Yeah, but this is outdated. That's not true anymore.
What was the answer? What did
David Merman?
David Merman did.
Yeah.
That's right.
Yeah.
But it comes from this quote. If I were forced to sum up in one sentence what the Copenhagen interpretation says to me, it would be shut up and calculate. But I won't shut up. I would rather celebrate the strangeness of quantum theory than deny it, because I believe it still has interesting things to teach us about how certain powerful but flawed verbal and mental tools we once took for granted continue to infect our way of thinking in subtly hidden ways. I've always loved this because in the end, it was re-expressing things, it was uncovering the flawed but powerful mental tools that ultimately caused David in 2012 or so to take up QBism himself. So there we are. Shut up and calculate was something he didn't want to do. He thought that the trouble with quantum mechanics was in uncovering, or the difficulties in trying to understand what quantum mechanics is telling us, is what had more to do with uncovering prejudices that we had from previous physics. So what is this thing called QBism? It was a project that was started in the early 90s, really, around 1993, 30 years ago, when I was first a student with Carleton Caves, and Rudiger Schock was a postdoc with Carleton Caves. And Carl was deeply under the influence of a man named E.T. Jaynes, Edwin Jaynes, who promoted not only things in quantum optics, but also a Bayesian view of probability. And Jaynes was instrumental in our thinking already back then because he had this attitude that we had never seen anywhere else. Our present quantum mechanical formalism is a peculiar mixture describing in part laws of nature, in part incomplete information, all scrambled up together into an omelet that nobody has seen how to unscramble. Yet we think the unscrambling is a prerequisite for any further advance in basic physical theory. For if we cannot separate the subjective and objective aspects of the formalism, we cannot know what we were talking about. Now, this was refreshing. Yeah?
I was always wondering about the year of this quotation from James. Is it from the 50s or the 60s?
It's from the late 80s.
The late 80s.
Very near his death.
Very late.
He died in... he died before I left Albuquerque.
And nobody spoke about the omelet before him? I mean, really?
Not that I know of.
John Bell at some point has that, no?
I don't think so.
No?
He said, so what's interesting about Jaynes was he said it's that quantum theory is a mixture of two things, subjective and objective. Instead of the usual game that people play in the interpretational business is to just take every term in the theory and assume it has something to do with reality. And it was Jaynes who first said, no, maybe some of the theory has something to do with reality, but other parts of it have to do with us. So we took this as our guidance, and finally in 2002, we made a public statement about how quantum theory might be better understood if we understood probabilities from a Bayesian point of view. Bayesian point of view about probability is something that Jaynes thought could clearly be identified as subjective. So the quantum probabilities would not be part of the objectivity of the theory. Other parts of it might. So that was the idea. You can see that we were all a lot younger then, and I had no beard at the time. Now, one of the fruits of that game, trying to clarify quantum mechanics in that way, was that in opposition to what you'll hear from people like David Wallace and Chris Timpson, we found that it had immediate explanatory power. There were a number of phenomena, like the no-cloning theorem and quantum teleportation, that one could understand immediately without any crazy story about signals going backward in time and then forward in time, or other odd stories. Or in a way that gave this one explanation, but this another explanation, and this a third explanation. It had immediate explanatory power in the sense that it unified all of these phenomena. That made it look fruitful as a venture. A physicist would say, if I've got immediate explanatory power, let me see if I can apply it to understand something else, and then something else, and so forth. The interesting thing that happened to us, though, that we hadn't foreseen, was that in trying to make sure that we genuinely had a consistent point of view. It made us climb the scale of Bayesianism, or move in the spectrum of Bayesianism, from the kind of Bayesianism first adopted by James, which some people call objective Bayesianism, to a more radical form of Bayesianism, that adopted by Bruno De Finetti. And this was, we were sort of forced there. None of us wanted to go there, not initially. After we got there, some of us started swimming in it. It was like, oh, this feels good. But before that, we weren't. So everybody knows this quote in the beginning of De Finetti's 2 volumes. He says, my thesis, paradoxically and a little provocatively, but nonetheless genuinely, is simply this: probability does not exist. In other words, probabilities are never factual features of nature. There is no such thing as a right or wrong probability. There's just an agent uses the probability that they deem best for them. And then only in that sense is there a right or a wrong about it. Now, what are the implications of this? Well, you just look at what you do with quantum states. From quantum states, you calculate probabilities. This we all learn in the textbooks. But once quantum information came around, people started to understand better that reciprocally, if you consider a robust enough set of measurements, the probabilities determine the quantum state. And if none of these probabilities are ever factual in nature, and quantum states are determined from them, it meant that quantum states are not factual in nature. So the ghost of De Finetti would say, my thesis, paradoxically and a little provocatively, is simply this: quantum states do not exist. So this idea of separating the subjective from the objective, that was the beginning of QBism. Then trying to be absolutely consistent about it led us to a more radical form of Bayesianism. And once we were settled on the more radical form of Bayesianism, it said something about quantum states. It really banished them from the world. Well, consistency kept going further and further. In order to make sure that this was airtight, a quantum state is an agent's personal judgment. In order for it to have consistency, we recognize that measurement operators, these things that we write down as Hermitian operators, they too were agents' personal judgment. Even unitary evolution, Hamiltonians were personal judgments. Probability assignments are judgments, and so it went. So eventually, we built up about 8 tenets, if you count them in a way that makes the title work. And it was all forced on us by consistency. But maybe the most radical thing that QBism did was in trying to understand this question. So these probabilities are subjective Bayesian, and because the probabilities are subjective Bayesian, quantum states are, and because quantum states are, Hermitian operators are too, and because Hermitian operators are too, unitary evolutions are. All of this keeps going on. But what are these probabilities about? James, when he was pushing this point of view, thought that quantum states were Bayesian, essentially Bayesian degrees of belief about states of reality. Well, that's not consistent either. And in fact, I think that some of the no-go theorems that have arisen in the last 10 years, for instance, the Pusey-Barrett-Rudolph no-go theorem, actually are evidence in favor of QBism, because they say you cannot take quantum states to be epistemic at the same time as thinking they are epistemic about pre-existent values. Now, you can give up one or the other. Most of those guys want to give up the idea that quantum states are epistemic. People like Rob Speckins and me say, no, hold on to the idea that quantum states are epistemic. You give up the other thing. So in that way, it's evidence for QBism, I'd say. All right. Answering this question was more difficult, but answering it was really the final step leading to QBism. And I think it's not better expressed than in a letter that ex-Supreme Court Justice Oliver Wendell Holmes wrote to a friend in 1929. He said, Chauncey Wright, a nearly forgotten philosopher of real merit. Who's ever heard of Chauncey Wright in this audience? Not even Michelle. So Chauncey Wright was a fellow that hung out in Cambridge with William James and Charles Sanders Peirce, but never obtained an academic position of his own. But he was influential on the two of them, and also apparently on Oliver Wendell Holmes Jr. Chauncey Wright, a nearly forgotten philosopher of real merit, taught me when young that I must not say necessary about the universe, that we don't know whether anything is necessary or not. So I describe myself as a betabilitarian. I believe that we can bet on the behavior of the universe in its contact with us. When I first ran across that quote, I was so pleased because QBists didn't want to call themselves Bayesian anymore because 99% of Bayesians thought that the Bayesianism QBism uses is too radical. So we sort of floundered about what the B should stand for. And then I found this term by Holmes, betabilitarian. It's about betting, and it's about betting on the universe's contact with each of us. And I thought that fits it to the T. And so briefly I thought, well, we'll just call it quantum betabilitarianism. But that was so ugly that ultimately I decided QBism is just QBism, and that's that. The universe is in its contact with us, I would say now in better language that we've developed since then, would be lived experience. The probabilities are not about what is out in the world when we write them down in quantum mechanics, but they're about the experiences that the agent writing down the probabilities is concerned with. So here's the whole story of QBism in a cartoon. Captain QBism Comics. So the story of when we adopt the formalism, when I adopt the formalism or you adopt the formalism of quantum mechanics, what are you adopting it for? The story is there's always an agent in the comic book. There's not just the universe in the comic book and stars and nuclei. There's always an agent. And the agent can take actions on the world external to his or her or their selves. I'm taking an action on the world. I'm lifting this thing up. But I can't always predict the consequence of the actions. Consequence is the experiences that are relevant to me. So the quantum formalism describes actions that an agent can take on the world in terms of positive operator valued measures. A quantum system is always assumed to be described by some Hilbert space. In this case, I write an H sub d. I'm always playing the game of finite dimensional Hilbert spaces. An action is represented by a POVM, and the consequent experience that the agent has from taking an action on a system is given by the choice of one element of this operator.
Sorry, why do you restrict yourself to finite dimensional Hilbert space?
Oh, because I think that infinite dimensional ones are misplaced, and it's a different theory, and I don't want to invest in a theory that I think is probably wrong. There's plenty of evidence in the literature that you can't get the infinite ones, as opposed to what the founders thought. You can't get the infinite dimensional Hilbert spaces as a limit of finite dimensional ones. And I think presently in mathematical physics, the consensus is there are actually two different theories. So the great mathematical physicist Pekka Lahti says, well, they're just different theories. I'm like, oh, that is so great, because it means, and he says, the infinite dimensional one is right and the finite dimensional one is wrong. And I was like, no, just the opposite. That's why I got excited. So I think the finite dimensional theory is probably the right thing, and the infinite dimensional one is some mathematician's dream. So I usually restrict myself to that unless I'm forced otherwise. And what is this entity? Well, the claim is that really it's living up in the head of this person. And it is the compendium of bets or gambles that this person would make about the consequences of the action that they take on the system. Why is Laura? Oh,
It's okay.
it looked like you disagreed with something.
No, I
If you did, feel free.
No, I was thinking. It's okay.
Okay. All right. I probably don't need to do it with this audience, but very often I do, and especially since I just read one of Hervé's papers, it feels right to do this. Imagine that I pull out a big eraser and I start erasing this piece of the diagram. So I've erased to some extent this side of it. I have left this behind, but I've erased the agent out of the picture. The question that I usually have to ask an audience, and I don't suspect I do here, but the question I often ask general audience is, if I were to do this, what happens to this? Now, an Everettian would say, look, this is just a component in the wave function of the universe. So, of course, these things stay behind. In QBism, they go poof. They don't exist in the universe. There was never a wave function. If you imagine that we are the first civilization, which is probably not a good imaginary game, but suppose that we here on Earth are the first and only civilization ever in the universe, then there was no wave functions before 1926, according to this view. And then afterward, whatever the opposite of poof is, some wave functions came into existence. For instance, when Schrödinger did his analysis of the harmonic oscillator in a 1926 paper. So I put this diagram to say, please take me absolutely seriously. There are no wave functions in the universe. They only arise when users of quantum theory arose. But in this diagram, of course, I left this behind. There's a sense in which the world is left behind. It may not be the same world that was there, because presumably, when we've got this is certainly an active component of the universe and shapes things as it goes along. And in the diagram without that, this is no longer here. It's not exactly the same world, but there's some of the world left. Okay, I said that when we developed QBism, for consistency, we went from quantum states being subjective to Hermitian operators being subjective and so forth. And I call it an eightfold path. One should take it literally that just as with the Buddha's eightfold path, this is meant to be a prescription to relieve the suffering surrounded, that one is surrounded by at Quantum Foundation's conferences. But that leaves open the question of what is the noble truth, or what are the four noble truths that give rise to this particular prescription. In my own words, I would say, well, what this is asking is, what is the ontology? What kind of world are we in? What kind of world are we swimming in that causes us to want to use these notions to relieve the suffering? And that's QBism's present quest. So I think the title of the talk was QBism, Where Next? That's where we need to go. But I'm not ready to go there yet. And I came here to study French philosophy for 17 days. And I'm not sure that that's where QBism needs to go yet. I'm ready to be convinced if it is a helpful direction. Or I may find that I don't think it's helpful, and I'll retreat to the warm comfort of William James and John Dewey again. But, so, here's what I want to do. I want to tell you about my attitudes, and for that I need to tell you more about QBism. And in particular, one of the best fruits of this attitude, I think, is a new understanding of the Born rule. And this, to me, has to play a crucial role in finding this ontology to go with the theory. So I'd like to spend some time getting you to understand the Born rule from the way we think about it, we being the five of us in my group. And then ultimately I want to tell you how that fits with the quest for a noble truth. but this part of it's going to be on these two pieces here. If I were to pick a single metaphor for how to express what QBism is about, I would choose this book from Leonard Savage, The Foundations of Statistics. I chose it because it was the first book written, as far as I know, on formalizing decision theory, how to gamble if you must. It was the first book that really laid out the foundation of using probabilities and utilities for expressing what actions one would decide to take. Normally I like to carry that book around with me, but I didn't bother to carry it here, so I brought a book by Merleau-Ponty, about Merleau-Ponty. Just imagine, if you will, that this book in my hands is that book there. And I want you to entertain the following ridiculous conversation. And it should strike you as ridiculous. So I'm carrying this book around and I say, I found this in a used bookstore. It's an old book, but it is fantastic. It teaches anyone who uses the book how to make better decisions, how to not do stupid things. And I tell this to a philosophy of physics colleague, not that I have any, but a philosophy of physics in the Western culture in America. And I say, here, you use it. And they'd be like, why do you want me to use it? I told you, this is going to be a ridiculous conversation. But I try to offer this book to my philosophy of physics friend, and I say, well, it'll help you make better decisions. Decisions about what? Things that matter to you. So here, you will enjoy it as much as I did. No, I wouldn't. It tells me how to make decisions for me, but does it tell me how to make decisions for you? No, it doesn't tell you how to do that. Oh, then if I read this book, I don't believe you exist? Of course not. By reading this book and learning how to make better decisions for yourself, you would never imagine that wipes me out of existence. Ridiculous conversation. You'd never think about it for a decision theory book. Okay, so then I finally get the guy to accept this, and he says, okay, I can see that this is a useful calculus, but I can't find anywhere in the book how to derive my existence. And I said, well, why would you expect to be able to derive your existence from a tool that you use? This is just a tool that you can use. Of course you can't derive your existence. You can look through all of the mathematics, and you are the thing that comes before using the book. Then they say, as a philosopher of physics would, oh, well then I need to know what can be a user of the book. And I said, well, do you feel that you can use it? Yes, I feel I can use it, but the book should tell me exactly who a user of the theory is. It should tell me what chemical composition goes into making a sentient being. And I said, well, okay, let's look in the introduction. And actually, if you do read the introduction of this, it says, a fit user of this book should know some elementary calculus and always have a pencil and paper in hand so that they can do side calculations. Okay. All of these objections people make to QBism. And I say, look, QBism views the formal rules of quantum theory as an addition to that book. And so therefore, if none of those criticisms apply to this book, then they don't apply to QBism either. In particular, let's imagine that Savage lived longer and he added some appendices to the second edition. So there's the book in first edition. In second edition, maybe there's an appendix A. Special considerations for decisions in love and marriage. Extra techniques are added. Appendix B might be special considerations for making decisions in the economic forum. Appendix C, special considerations when making decisions about actions taken on your external world. So the view here is quantum theory is only an addition to this book. In fact, it's an appendix to it. This is the foundation of it all. And the thing that it adds is how to gamble if you must. Like the whole book is about how to gamble if you must. How to gamble if you must in a participatory universe. And in such a universe, you must. So when I get to the end of the talk, we'll come back to what this could possibly mean. All right, now let's start thinking about how to think about the Born rule from the point of view of QBism. Its foundation really is that book, but also this nice statement by Dennis Lindley. He says the topic studied in that book is a situation of an individual who is faced with uncertainty about some events of concern to him. All of us find ourselves in this position. We are born into a universe for which we all have uncertainty. That is the basic given of QBism. De Finetti's task is first to recognize openly the uncertainty surrounding us and then see how we can best understand it. The main result is that the uncertainty can only be described satisfactorily in terms of probability. So uncertainty is a more basic notion. Probability theory is about how to handle uncertainty. The coherentist paradigm is egocentric. It is the tale of a single person contemplating the world and not wanting to be stupid. He realizes that to do this, his statements of uncertainties must satisfy the laws of probability theory. So, living in an uncertain world is the basic thing. Deciding not to be stupid is the next step. And then seeing that deciding not to be stupid implies that you should use the probability calculus is the third. Here's a way to quantify that. This is called the Dutch book argument. And here the setting is that there is a bookie and a gambler. And the bookie posts numbers. What are these numbers? These numbers are prices for tickets. Word probability is never mentioned yet. They're just prices for tickets. When the bookie puts this number P sub E, he is declaring that he will buy a ticket that's worth $1 if the event E occurs for any epsilon less than that amount. And the bookie will sell the ticket for any epsilon more than that amount. So that's basically his pricing scheme for this ticket of this structure. If you take epsilon to 0, then it's just equivalent to a bookie is willing to buy or sell the ticket for this amount. Okay, so this is the price of a ticket. Nothing about probability. Similarly, the bookie might do some funny things like put a pricing for a ticket that is worth $1 if not E. This is the price of that ticket. They're independent tickets. The bookie could write down, this is the pricing for a ticket that pays $1 if either E or F, etc. So there's this list of pricings. Now, what would be stupid? Stupid would be if the bookie wrote prices down such that a gambler could walk up and he says, I'll buy some of the tickets at this price. I'll buy some of the other tickets, the other ones, for not E, at this price. I'll sell some to you at this price, and so forth. If the gambler has a selection of buying and sellings of the ticket such that no matter what happens, the bookie will lose money, then that would be stupid behavior. De Finetti recognized that if you just add one rule, never declare numbers that will lead to a sure loss, a loss no matter what happens, then it turns out the only way that can be satisfied is if these statements satisfy the usual rules of probability theory. It's an if and only if statement. There's only one way to ensure that a sure loss can't happen. You may have a loss, generally, but a sure loss, one that will happen no matter what occurs in the events, there's only one way to get that. So this tells you a way of reading probability theory that you don't usually see in the elementary textbooks. It suggests a normative reading of probability theory. The bookie has prices for tickets that they're willing to publish, but the prices may have arisen from various sets of considerations. Not like in a textbook. In a textbook, they say, here, given this, prove this. Given this, prove this. In the real world, you've got to come up, a weather person has to come up with all the different probabilities that they might assign. And it may be, for instance, that the weather person follows another weather person from the Washington Post to arrive at these numbers. What's the major newspaper here? Le Monde? Is that a... So, and they find that actually they trust the advice and the data from this other newspaper, Le Monde, and get this number from that. This is Washington Post, this is Le Monde, maybe this is New York Times. And De Finetti's idea or point is initially these numbers may not fit together according to this equation because they come from different sources. But an agent would be stupid if he just let it hang like that. It would be better for the agent to readjust the various probabilities to try to make them consistent with this equation. As William James and Bas van Frossen have pointed out, that sometimes involves the will. You've got to hammer these things into the equation. They don't always initially fit. And so from that perspective, each of the terms in this equation are subjective. There's a voluntaristic element to it all, Van Frossen would say. I don't think James ever used that term. But there was a kind of thinking that was on his mind. Subjective. Yeah.
The will story comes from von Weizsäcker, right?
From?
Von Weizsäcker.
About?
Not from von Frossen, from von Weizsäcker. Yeah, I know.
I'm thinking of Bas van Frossen's paper, Belief in the Will,
Yeah.
really, where I'm putting that. But not everything is subjective. So I had 3 subjectives before, but the norm is agent independent. It's something that's invariant for all agents. Every user, every person who wants to not be stupid should pick up this book, and they will learn that this norm should apply. And another person who picks up this book will learn that this norm should apply. This book doesn't tell them about the individual elements that they put in these places, but it says that the relation should hold. In that sense, I'm willing to call this a third-person element of probability theory.
Here it's really a critical point because this kind of norm is an intersubjective norm. Any agent who wants not to avoid sure loss should use this formula. But I know that you want sometimes a little bit more than this intersubjective criterion of agreement.
Mm-hmm.
You want an intersubjective agreement about what we are in, what we participate of, namely the world. So this is, to me, there are two ways of putting objectivity, 2 ways of putting third person.
Yeah, indeed. I think this is more than intersubjective agreement.
Yeah. Even that?
Yes.
Not that.
Even this.
Even this?
I think this is not intersubjective agreement. I think individually, I'm either going to lose my life if I publish numbers that don't satisfy this. An opponent can come kill me.
Mm.
Yeah.
And that I don't think has anything to do with the intersubjective agreement. So that's why I keep going further. I think maybe further than you want to go.
But I think Michel is saying something else. When the participate of argument means that when different agents come and look at this, they already agree on the fact that there is a book maker and that there are prices on events. They know what E means, what F means. So there is a big description of the world that is already shared. And they just talk about prices, but the E and F are already common knowledge.
Perhaps. I've got 17 days to decide on this sort of thing.
Look, yes, there is still something that puzzles me. This relation holds irrespective of what the probabilities are about. Irrespective of, anything that may arise during the famous interaction, measuring interaction. So for me, it's a norm of lower level with respect to the other norms that you pointed, such as the number 2 in Born's formula and so on. Can you distinguish between these two kinds of norms? For me, one is a norm of internal coherence of the system of bets about anything, and the other one is
Not
a little mark that shows that there is something more than that. And I think that's something more that you want to point out.
I think so. I think I'm going in the direction of talking about that. If I don't get to it by the end, then remind me, and we'll try to discuss it then. And I think this is maybe a little more. QBism views quantum theory as supplying extra normative rules to probability theory. So it's true that this is posed at the level of a kind of in a world independent way. But so is this, Savage's book.
Yes.
But then there is Appendix A, extra considerations for decisions in love and marriage. That now assumes that we not only have, now we've got this concept of love in the story. And when we get to Appendix C, now we've got this view of a physical world in the story. So that's why I say extra normative rules. They're only things that come in the appendices.
Yes.
Okay, so this gives the motivation, and this really is now we're getting to the meat of the talk and stuff that is, I think, new to most of you. This gives the motivation to try to understand the Born rule, the key thing in quantum theory for calculating probabilities in purely probabilistic terms. I want to find some way of understanding this that makes it look not so lopsided. I say it looks lopsided now because though I have a probability on the left, the entities on the right look logically prior to probabilities. They at least appear that way. And this, I think, leads to so much of the discussion in foundations of physics where people view these entities, a quantum state and measurement operators, as objective states of affairs. These are properties of things. And then consequently, you might ask, well, how exactly do you understand the thing on the left? Some people would say, well, then the probabilities are objective as well. Some people like Richard Healy will tell you an extremely complicated story that allows these things on the right to be the norms and the things on the left to be subjective judgments. I'd like to find some way of viewing this so that everything on the left and everything on the right is on the same footing, and so that we can see that it is a norm along the lines of, but not identical to, the Dutch book story. The hint comes from Richard Feynman, a 1951 paper, which I have always found amusing because it's titled The Concept of Probability in Quantum Mechanics. And then in the first sentence he says, despite the title of this paper, the concept of probability in quantum mechanics is the same as it is everywhere. And then he goes on to say, the new theory asserts that there are experiments for which the exact outcome is fundamentally unpredictable, and that in these cases one has to be satisfied with computing probabilities of various outcomes. But far more fundamental was the discovery that in nature, the laws of combining probabilities were not those of the classical probability theory of Laplace. Now, I myself wouldn't use exactly this way of phrasing it, but it's, I think, the key idea that much of what I'm going to talk about hinges on. He says the concept of probability doesn't change. And I would say that too. It was subjective Bayesian before, it's subjective Bayesian now. But in Appendix C of the book, we're going to combine probabilities in a way that we didn't in the first part of the book. So that's the key idea. Now, of course, he was thinking of the double slit experiment where you have, you've all seen this story. You've got the slits, you've got a detector, and Feynman in his discussion, especially in his path integral paper, it's clearer than the one where I took the photo from. In his path integral paper, he says, if there's nothing done at the slits, then we expect this pattern. But if we put detectors at 1 and 2, to see whether a particle goes there or there before arriving at the screen. We expect these two patterns. And what is surprising is that this is not the sum of those. Then he says in his book, we choose to examine a phenomenon which has in it the heart of quantum mechanics. He thought that this one thing alone had the heart of quantum mechanics. In reality, it contains the only mystery. I'm going to essentially argue the same thing, that this really contains the only mystery, and entanglement is secondary. It's not the primary mystery. But I'm going to do it in a way that's different than Feynman. His solution was to back off from probabilities. So despite what he said in the previous slide, the fundamental idea is that probabilities combine in different ways. He backs off from it and introduces amplitudes. And then he says these really are the more fundamental things, not the probabilities. And we can get probabilities from them. I don't want to do it that way. I want it to be purely about probabilities at the beginning and probabilities at the end. Among other things, by the way, for these slides, it really dawned on me I have to make, and I wouldn't normally make this distinction, but in this audience I had to. There's a distinction between the French philosophers of physics and everyone else in the world. So I even have a slide that I often put up with pictures of Tim Maudlin and David Albert and Wayne Mervold, and then I have them crying like little babies, saying, wah, 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 your quantum states aren't real. And that's their criticism. That's what it boils down to. Well,
but you know,
but French philosophers of physics don't go wah, wah, wah. They say, maybe there's something to what you say. You're very nice people.
We say, wonderful, your quantum states are not real.
But you know, that after that, Feynman changed his mind and recognized that it was not true in saying that it is the only mystery, and he recognized that entanglement was fundamental.
You read his quantum computing paper carefully, and he starts off with this same point, and then he says, I try to push it in a corner, and then he ends up with a Bell inequality. But you can still see in that paper, I promise you, that he's still thinking that it's interference that is the key idea. I'll show you.
Okay.
Well, okay, so I give this as an example of one non-French philosopher who gets, see here I said, introducing complex amplitudes distracts from the seminal point. Here's an example of it distracting. Powerful plausibility arguments have long been available to the effect that a quantum state is something real. They almost all have to do in one way or another with quantum phase, with the fact that the wave function in its relation to probability is strictly a generally complex probability amplitude. It has more structure than a probability does. Well, that's just wrong, and I'm going to show you that it's just wrong. That is a property of one representation used for quantum theory, but there are many representations of quantum theory, and one can find representations where there are no amplitudes anywhere in the story. So, when non-French philosophers, have such strong assertions, almost always it's based on the quantum mechanics they were taught in the textbook, and they never had quite the creativity to think outside of the box. So let me show you how to fix this. I'm going to call this the d-squared non-orthogonal slits experiment. I mean, this is a bit of a misnomer because there are no slits in this experiment, but it is very analogous to the Feynman story. So let me try to explain that to you. I have a setup here where I've got a quantum system that is going into a measuring device. I'm going to call this measuring device a reference measuring device. A measurement will be performed whose outcomes are the operators R sub I. That's if the measuring device is turned on. So that's like having the slits there but with no detectors when it is turned off. And having it turned on is having a detector at each slit. So a measurement is performed, and then depending upon which measurement outcome is gotten, a new quantum state, the system in a new quantum state comes out. I'm going to call it sigma I. And then that proceeds to a third measuring device. This device is like the one at the screen in the back of the Feynman diagram. So let's go back to that. So here's my quantum system going in, and then the first measuring device is analogous to having detectors here at the slits, if it is turned on. If it is turned off, it's like having no detectors at the slits. And then there's a final measurement back here that is just position. But now, in distinction to the Feynman story, this can be any quantum measurement whatsoever, not just position on a screen. It could be looking at the Fourier transform of the positions. It could be looking at anything whatsoever. Now, notice this thing in the usual quantum description. How do I get this thing aligned? Oh, come on. That doesn't work. That does. Okay, anyway. This is the quantum state going in. That's some operator. Then this device is described by operators, but this measurement determines probabilities, the probabilities for the outcomes. That's where my red dot is now. And for over here, we can talk about the probabilities of the outcomes, and we can talk about the conditional probabilities. I'm just going to use my finger. We can talk about the conditional probabilities for the outcome here, given the outcome there. Now, I have to be a little more particular. I already told you I'm going to allow this to be any quantum measurement whatsoever, not fixed. For this one, I'm going to fix it. There's only one measuring device in the picture, and it has to have the property of being a minimal informationally complete measuring device. And I'll tell you what that means in just a second. This is variable. Any measuring device on Earth, this is fixed from the outset. In a way, this is like choosing a coordinate system to do a physics problem. You fix a coordinate system, you choose one that is appropriate to a problem. For instance, if you're doing problems on a sphere, you're probably best to use spherical coordinates. This is going to be one that's particularly good for our problem at hand. Okay, what do I mean by these terms? Any quantum measurement and a minimal informationally complete measurement. Here I've got to go beyond the old von Neumann theory. In von Neumann's day, one called measurement a Hermitian operator. And what you do with the Hermitian operator is you diagonalize it. You find the eigenprojectors and the eigenvalues. And if you're talking about non-degenerate observables, then people usually associate the outcomes with the eigenvalues. But if they're non-degenerate, you could say, oh, what I mean by an outcome is the eigenprojector. So that's the way I'm going to view it here. I have a collection of projections. These are the eigenprojectors of a Hermitian operator. Because they are eigenprojections of a Hermitian operator, they're all orthogonal to each other, and they have the nice property that they sum to the identity. In 1971 or so, Alexander Kolovo and some other people independently said that this isn't really the best notion of measurement for quantum communication problems. There is a larger class of measurements that sometimes people call positive operator valued measures, or generalized measurements. And in that kind of scheme, a measurement is described theoretically by introducing a set of operators, any number, such that all of them are positive semi-definite, and they sum to the identity. So this theory is a lot like that theory, except when we're talking about a d-dimensional system, there's no longer a restriction that the set has to have exactly d elements in it. And this is now common day stuff for quantum information. It is not yet for philosophers of physics, at least in the non-French world, who want to ignore it for the most part in their discussions. And you can't disagree with me on that, because I'm the guy who has to fight with them all the time and see what they understand and what they don't. And even just a few years ago, a lot of people just think, this stuff about POVMs is not really all that essential. A good example is John Ehrman in a paper that had something to do about cubians. We're called cubians. And in the paper he says, these guys mention positive operator valued measures, but they play no essential role in what they're talking about. I don't even know why they mention them. A lot of people have been influenced by John Ehrman. Okay, so we're going to need this notion. And now, with respect to that, what I mean by a MEIC, a minimal informational and complete measurement, is a measurement such that the operators form a basis for the space of operators. So if I have a d-dimensional space, the operators live on a d-squared dimensional space, and I want a measurement whose elements span that space, and I'm going to call that a MEIC. So since the space is dimension d-squared, these guys have d-squared elements. So that's the setting. Frank, do you have any questions? Or you seem interested in the formalism.
I'm just agreeing what you said.
Okay. So here's the setup again. This is any measurement. This means any collection of positive operators that sum to the identity. And this is a MEIC. This is any collection of positive operators with d squared of them in the set. They sum to the identity, and they all have to be linearly independent. Okay, so once I've got this set up, remember I took Captain QBism and I took an eraser to him. I'm going to similarly put an eraser here. Here's what I'm going to do. I'm going to take an eraser and I'm going to erase the quantum state out of the picture. And for this measuring device, I'm going to erase all of those operators. And I'm going to erase these quantum states right here. And I'm going to erase these operators. So in everything that has a little cap on it, a little hat, I'm going to erase out of the picture. But I'm going to leave the probabilities behind. I didn't erase these guys. And now I want to ask, now that I've erased the quantum mechanical origin of all of the probabilities, can I still say how the probabilities have to be related to each other? Can I find a relation between this and this and this? Anyone want to venture a guess? Laura. You don't want to venture a
No,
guess.
you need an assumption of completeness. Otherwise you can't.
Well, I want to say, yes, of course you can say how they should be related. It comes from the regular Dutch book argument. If these guys don't satisfy the law of total probability, and these were some bookie's numbers posted on the board, if they didn't satisfy this relation, then somebody could gamble in such a way that it would lead to a sure loss for the bookie. So they have to satisfy the laws of probability, regardless of whether they came from quantum mechanical considerations or not.
But to prove this, you need completeness.
Well, completeness is part of the Dutch book argument. If what you mean by completeness is the
You need
probabilities
to know that there are
sum to one.
that there are d square of those guys and d of these guys.
No.
Yeah?
There are d squared of the.
Yeah,
so
these
P-
are POV.
our I's. It is assumed that there are d squared of these guys. These guys can be anything, from 2 to 300 million for dimension 2, even higher. So this is just any probability distribution, the ones that we had on the previous
Sure,
page.
but you need to know that these things are on the Hilbert space of dimension d, I guess.
No. I've erased all of that. All we do know is that there are d squared outcomes here.
Mm-hmm.
And there's any number of outcomes for this.
No, but the thing that you call this is a POVM on what?
We don't need to know that it was a POVM. That's what I'm telling you. We can forget. We like Michel, he was thinking about this diagram, if you'll allow me. He was thinking about this diagram as he was crossing the street near the Odeon. And he was thinking, all of these probabilities are of quantum origin. There are d squared of these, and there's any number of these. And he had it in his mind, and then he got bonked on the head. And when he got bonked on the head, miraculously, he remembered, I still remember these numbers. There's d squared of them. And I remember these numbers and these numbers, but I don't remember where they come from. And a bandit comes along and does something mean. They say, you have to be a bookie now. Put these numbers on your board. And if they don't satisfy this, then someone can lead him to a sure loss. Has nothing to do with quantum mechanics. It has to do with the structure of probabilities.
But basically what you say is just that when you manipulate probabilities, you just have to rely on this law of total probability in any case.
That's right.
Okay.
That is all.
Okay.
But you can see people get confused about it because they think quantum probabilities are somehow different. And now I'm going to show you a sense in which they obey different rules, but we got to change. We have to make things more complicated. And that's what I'm going to do next. Okay, so, but before we go there, see how this...
And again, you need the assumption that on the left you have an informationally complete set.
Not for what I'm saying here. All I'm saying is there's a list of numbers. There is just a list of numbers in Michel's head. And he has a table of numbers.
You need an independence assumption about the operators that these numbers came from.
No, sir, you don't. And it's just a trivial calculation. So the user of this book should be accompanied by some paper and a pen and work it through. There's nothing quantum mechanical in the law of total probability. As long as they're probabilities and they come, they have these conditions. One is a conditional probability. They have to fit together according to this. Has nothing to do with quantum mechanics. Take that as a given. We'll discuss it. We'll discuss it further. Notice I did say sir. When I said no, sir.
Yeah.
So
That's
yes,
right.
I strongly disagree with you, and it's just an elementary calculation. But you just need to do it. What if we turn off the switch? Now things are different. Because when we turn off the switch, there's no measurement here. That means there's no probabilities for the outcomes here. There's no P of Ri anymore. And consequently, there's no P of Ej given Ri, because there was no Ri anymore. Now the Born rule is the guidance. We've got Born rule as the guidance because quantum state rho goes in, quantum state rho comes out, and it goes into this device. And we've got these operators still around. And now we need to know, that we're talking about quantum mechanical stuff at this stage. But it looks like that setup is completely different than this setup. Dum dum dum. Or is it? And the answer is, once again, an elementary calculation, not one that people do much, but a simple manipulation can calculate the probabilities in the switch off experiment in terms of the probabilities that arose in the switch on experiment. But look at this. This had a probability equaling the product of the probabilities. This is a vector. Oh, I didn't explain, I got sidetracked. So in this notation, this is a vector of a certain length, of length n. This is a table of size n by d squared. And this is a vector of length d squared. So I've just found a better notation for this. I'm writing it as a matrix equation. I'm going to do that again. In this case, I can write the probabilities of the experiment where the switch is turned off in terms of the probabilities when the switch is turned off, just by modifying the equation a little bit. I introduced this new matrix phi that I'm going to call the Born matrix. These are positive operators, so therefore all of these numbers are non-negative. When I invert to go up here, then some of them turn negative.
So basically what you're saying is, instead of writing an expression in the Hilbert space of dimension d, let's go to the Hilbert space of dimension d squared. In that case, then our matrices will become sets of real numbers between 0 and 1, and we can still get the empirical facts as before.
Yeah, that's right. If what you mean by empirical facts or the
Yeah, the left side.
Okay, yeah. Now this is completely general. It's not just like the double slit experiment, talking about one experiment. It talks about every possible kind of measurement that can be performed over here. There's no operators or state vectors that appear in these tables, not a priori. There's no complex numbers. So here's what we get. The upshot of it is we've got this equation now, where the stuff on the left refers to the switch-off experiment. The stuff on the right refers to the switch-on experiment. And there's no contradiction to the law of total probability because the law of total probability doesn't compare two experiments. It's only about one. This is a direct comparison between two experiments. So we've got the Feynman picture again. Essentially, we've got this situation versus that situation, and the connection between them is this new equation. But once one has this new equation, you've got the impetus to say, if you're a QBist, ooh, we should think of that. Oops. Sorry. Let me go back to, actually, this is something Alexei just pointed out. Essentially, the old Born rule is still visible in this. So here we had the quantum probabilities. In the old Born rule, we had trace of the quantum state times operators. Well, this represents the operators. It's a probability table, but it represents the operators. This represents the quantum state. So the old rule was bilinear. This is still bilinear, or at least convex affine, as it's called. So, but it's still there. It's just kind of hidden. But QBism says read it normatively. That's the conceptual step. QBism says, oh, it's not that these terms on the right are more fundamental than that. They're not. When an experimentalist goes into the laboratory, they may have a good sense of what they can get for this. And maybe not such a good sense of what they would get for these other things. So it might be that an experimentalist is more confident of this initial estimate than they are of these two. And what the Born rule is telling them is adjust all of the numbers so that they fit together according to this. To make them fit often involves the will. And here I cite the great philosopher, experimental physicist Jeff Kimball, who once told me that when you walk into the laboratory, this is why I keep doing this, he's a Texan. He says sometimes you have to hold a gun to the head of nature and say, you will do what I'm telling you to do. So sometimes you have to fit these guys in perhaps a violent way. All right. So there we have the Born rule written in a way that is normative. What are the conceptual implications of that? Well, before, when we saw that probabilities not existing means quantum states must not exist. What time did I start? I'll finish 20 minutes or so. Is that okay? 15 minutes? Okay. This is protection. I never like discussion, so I'm protecting myself.
Right, we have to leave at
Okay.
7.
Okay.
So see if we want to have
you've
some
got
time
it.
for discussion.
So I said that the implications of probabilities not existing are profound for what quantum states are. Quantum states can't exist either. Well, look at this. This represents a measuring device. Now, Bohr would tell us that a measuring device is this solid object that's out there, very heavy, has it bolted to tables so that it's very classical. And QBism says, well, a measuring device conceptually is a conditional probability distribution. So if you think that probability distributions are less substantial than those things, that's what QBism is saying.
Bohr would not say that.
I bet I've read him more.
Yeah.
But how?
Doesn't mean you're going to trust my opinion, but I bet I've read him more.
how does it fit with your very concrete picture in which the agent is, pushing its hands towards something?
Yeah. So let's talk a little bit about exactly that. Michelle has heard this story before, maybe Laura has heard it before, but I was at L'Etoile once, and there was a crazy woman somewhere over here, and she said, "How do you get across?" And I said, there's a tunnel, and we go under the tunnel. And she said, "Oh, I'm going to run for it." And she ran across the thing. From the point of view of QBism, that is taking an action on the world. And taking the action on the world could have led to various consequences. Among other things, that agent could have experienced great pain or death. She made a decision. She made a decision to run across, to make this action, rather than the more sane decision that I made, which was to go through the tunnel. Luckily, she survived. We met each other on the other side. And she said it was exhilarating. Well, that was a consequence or an experience that I hadn't anticipated for myself. QBism doesn't draw any kind of distinction between that as an action on the world and working in a quantum optics lab and taking actions on the world with all of these devices. They are conceptually the same. The difference is, in the case of being at L'Etoile, a person made a snap decision without the use of probability theory. But it would have been to her greater benefit to sit down for a little while and think about her chances of surviving if she ran across. So the option of using probability theory was there, but in her case she didn't want to use it. In other cases, maybe you don't have time to use probability theory. Similarly with quantum mechanics, very often, so even though I can say it would have been to her benefit to use a little probability theory before making her decision, it probably would not have been to her benefit to use the full calculus of quantum theory that draws a distinction between these two experiments. But in some cases, it's absolutely necessary. And what we've just learned is that the things that we call the measuring devices really are conceptually part of the agent who's making the gambles. Now, that leads us into the territory of phenomenology. But I'll have to be educated if it's true. Okay, I'm going to cut my talk short now. I'm just going to say the key thing that we've learned is that the Born rule can be written this way. It can be understood normatively. And one of the things that comes from it is that the agent should be, because this is a probability assignment of the agent, and is the agent's expression of their action on the world, this is part of the agent, it's not separate. The minimal difference between this equation and the other one, the law of total probability, I would say captures the essence of quantum mechanics, and this leads to a technical program that I'm not going to describe here of trying to find the minimal difference between these theories. This phi, remember, depended upon a measuring device, a reference measuring device. Ultimately, we'd like to mod out that and find the one that leads to the minimal difference of these things. It's kind of like finding a value of h bar in QBism, and there's an answer, and it involves a mysterious mathematical structure of which no one really knows whether it exists or not, but it's known now to exist in all dimensions less than 193. Most people who work in the problem think that this mathematical structure always exists. But it's been shown recently to have something to do with Hilbert's 12th problem. I'm not going to talk about that. And it leads to this. This is the upshot of it. The Born rule, now writing it in component form again, can always be written in this way. Okay. Let me end the talk with some philosophy. QBism's view is how to gamble if you must in a participatory universe. What are we really meaning by a participatory universe? And to my mind, the best expression I've ever seen, simplest and clearest for what at least this QBist has in mind, is a play on John Wheeler's diagram due to my friend Amanda Gefter. So in place of the beginning of the universe leading to an observer, and the observer acting back on the universe, Amanda's has a tree out in the forest, and someone there, and story goes like this. You have a subject and an object, and mostly they seem like separate things, but when you look closely enough, you find that they are conjoined, that there's this piece of connective tissue where they can't be pulled apart, because within that region, there's no way to say which is which. So they look like they're separate things, but if there's a little piece of connective tissue down here, that if you just focus in on that, you wouldn't know how to say what is the subject and what is the object, not a priori. The discreteness we find in quantum mechanics is not a property of the object, it's a property of the subject-object relation. I think a useful way of thinking about this is to see Planck's constant of action as a kind of coupling constant between subject and object, between observer and observed. As you turn the strength of that coupling down, the area of the overlap gets smaller and smaller, and if you turn it all the way down to zero, observer and observed can be neatly separated. It recovers classical physics, and it frees the object from its subject so that it can be shared by other subjects. So if we turn H all the way down, we ultimately get a connection, a disconnection between them, and now we can think of an object as being shared by others, and we can start thinking of this as existing independently of these other entities. But of course, H is not zero, and so we have to contend with the irreducible coupling between subject and object that QBism says is the very essence of quantum mechanics. So I think she's onto something here, that really what's going on, what we mean by participatory universe, is that this disconnect cannot be made. That there's always some sense in which, in my diagram, in which the object and the action that the agent is taking on it are not so distinct after all. And the little flash that is a quantum measurement is something that's between the two. Now, there's a number of philosophies, then, if one takes that idea seriously, that one might base an ontology on, and I just give a list here of some. James's pure experience, he wanted to see pure experience as the stuff of the world. Whitehead had his actual occasions, that he thought was a mathematization of what James and Dewey were talking about. Dewey and Bentley's late notion called transaction, Merleau-Ponty's flesh, and the chiasma. Is that how you say it? Chiasma. Karen Barad's interaction, Mach's world, elements. I'm impressed by all of these philosophies to lesser or greater extents, and I think that maybe there's some useful ideas in all of those philosophies, one of which I'm going to devote myself to for the next 17 days. But none of these, I suspect, depend upon the exact insights earned by the quantum theory. And really, to get it right, I don't think it's good enough to say, oh, Merleau-Ponty anticipated QBism. He really has the right picture if he does. Because it's not detailed enough, not for my tastes. We have to have, I'm a physicist, I'm not a philosopher. I have to end up with some new physical insight that I can use. So, what would that take? What has to be sought, I think, is some kind of pure experiency, fleshy, interactional world elements, I'm just throwing them all together, whose characteristics are informed by this thing that I want to call the QBist version of the Born rule. The distinction between classical and quantum is to understand that those two experiments, switch on and switch off, are different, and that the difference matters, and that it indicates that an agent is more involved in the world than one thought of classically. So I would like to walk up to just the right set of philosophical ideas and gather from them, how can you help me better understand this equation and understand what is more particular about quantum theory than is in those philosophies. QBism is a long project. I told you that it started 30 years ago in the spring of 1993, and I don't expect everything to be settled this week, but that's where we are, and that's where I think we're going next. Thank you.
Thank you very much, Chris.
Yeah, now you have 34 minutes to torture me.
Is it
And then me.
is it
And we'll do.
will do. If I may, have a comment and question. My comment is that following what you said at the end,
This is better than Carlo Rovelli. He always has a question, but they're really comments.
I don't want you to answer that, but that's just a comment. The reason why it's often asked what is an agent, but you don't like to define, as you said, when you read the classical probability theory book, you don't have to define what is the user of the book. And you're right, in the classical probability theory, there is no need to define the user of the theory, because what happens, what you bet on, is something totally external to the agent. In your case, as you say, and I agree with you, what happens is not independent of the guy who is going to use the theory, because it's a participatory universe. And in a way, the agent is creating what happens. That's not the case. When you throw dice, you are not participating to the result, which face on which the die is going to fall. When you do a quantum experiment, then you have something to do with the result, because the result is not there independently of you. So you are really playing an active role. And this is why it is often asked, what is an agent? Because the agent is not just a passive witness of the result. But that's a comment, and we already had this discussion, and I still maintain that it's different from the classical probability theory.
Yes.
Okay.
And I still maintain that you're drawing a distinction that shouldn't be a distinction.
Okay.
For instance, one thing that attracted me in these directions was being called an American pragmatist by, am I in the right place?
No, it's okay.
Being called an American pragmatist by Matthew Donald at a conference in 1999. And I thought, what is an American pragmatist? Didn't know. And then I, by complete accident, came across a book by Martin Gardner, who you probably read in your youth like I did. Wrote in the book there was an essay, Why I Am Not a Pragmatist. And then he describes why he's not a pragmatist, and among other things, he talks about a case where you have a card on a table, you turn it over, and it was Queen of Hearts. Before you turned it over, you didn't know it was Queen of Hearts. But it was the Queen of Hearts, and you just learned it was the Queen of Hearts. And then he said, but no, James and Dewey would never talk that way. They have this convoluted way of saying that it has become the Queen of Hearts in the verification process. And there's no need to do that. It complicates life. You can express everything that James and Dewey are talking about in the old language of, when I turned it over, it was Queen of Hearts. I saw Queen of Hearts because it was Queen of Hearts. Mm-hmm. And I thought to myself, wait a minute. If we were talking about a quantum spin, we wouldn't use that kind of language. Why is it that we're drawing this disconnect? Well, already James and Dewey saw that perhaps we should always be talking about experiences. And so when you said in the classical case, the agent is not involved because these are not experiences, these are facts, and the probabilities, we're gambling on things that happened or didn't happen. without the involvement of the agent, already in 1898, James would have rejected that idea. And actually, they are on the same footing. And I kind of think that one of the lessons that we should learn from quantum theory is we shouldn't have that old vision, even for the classical world. Ultimately, we learn something from quantum theory because, as Marcus Appleby says, it has all of the same problems, but it wears them on its sleeve. So, I don't think there's such a distinction. I think that one could take the book of Savage, talk about experiences throughout, and it wouldn't change the calculus. And you think, oh, it does change the calculus, but no, it doesn't change the basic calculus. So I'm going to continue to disagree with you, that as long as we're talking about the decision theory level or the usage of quantum theory, then agent is the user of a book, and as Jacques Pinard likes to say, what is a handle? A handle is something that you can use as a handle. If you're not something that can use it as a handle, then what makes it a handle? Similarly here with quantum theory. Maybe that wasn't so clear. I'll give you a reference to Jacques' talk.
Okay. So okay.
Did I beat you down? Or?
I go on. Okay for that. I'm not totally in agreement, but we can continue discussing elsewhere. And just one question, and then I'll open.
There is Lev online.
Yeah. So Lev, I ask just one more question, very fast, and then I give you the talk. And the question, and we discussed that just before your talk, and I know that you have no direct answer to that, but it would be really interesting in order to better understanding the ontology of QBism, if you could precise if the external worlds that each agent interact with is the same for all the agents, or if each agent has his own external world that is relative to him or to her. And that's one question I have already asked, but that is a very important point to really understand what is below. And I don't know if I know that you don't have a direct answer to that, but that's an important question I think that we have to discuss in order to better understand what you mean.
Yeah. Oh, okay, in this case, I agree with you.
Okay.
In this case, I agree with you that we need a better understanding of this. As we were talking about it when we went for coffee, I think that QBism is a mixture of first personal and third personal. And I think that's the direction it points in. That not everything is first person, but it also says that first person is something that you can't derive out of a purely third personal picture. So when we bring it down to this question about is it my external world or is it everybody's external world, my tentative answer is that there are some aspects of QBism that refer to my external world. When I perform an action, I'm performing it on my external world, purely first personal. Is there also a sense in which there is a shared world that runs deeper than just intersubjective agreement? And I think there's also that. So I don't think that one needs an exclusionary view that is everything is first personal, everything is third personal. I haven't been unconvinced. Maybe my 17 days here will unconvince me.
Are you sure?
I still haven't been convinced of the necessity of completely dropping all third personal items, nor the desirability of dropping all third personal items. It may be that you can construct a completely first personal account of everything and it's consistent. But the pragmatist in me wants to know whether it is useful. And I'm not convinced that it is always useful without just falling into some kind of feeling for, well, I understand this theory. I always want every one of our physical theories to be the stepping stone to the next. And for that, I tend to follow Einstein a bit when he talks about his program of the real. That the program of the real helps you make the leap to the next level of physics. And what he meant by program of the real was a third personal picture of things.
That's a question that we have to continue. That's interesting, yeah. Lev wanted to ask a question.
Okay, now I also see you and hope you hear. So, thank you for the talk. And you say that the essence of quantum mechanics is the world. Yes?
Yes?
And now I hardly hear you. So when you reply, go to my microphone. So for me, the quantum mechanics are two things. First, it's unitary evolution, and second is the Born rule. And the Born rule is needed only when I perform a quantum experiment which might have different outcome. If I prepare up Z and measure up X and measure spin X, I need the Born rule. But if I prepare up Z and measure up Z, I don't need the Born rule. So I can imagine a Gedanken universe in which I never do quantum experiment for which I'm not sure about the outcome. And I can assume that the nature also doesn't do this kind of thing. We only have unitary evolution, what sometimes I call a tale of a single world universe. I believe in many worlds, but the many worlds will happen only if we perform a quantum experiment with possible different outcomes. But somehow initial conditions are such that we never do this. We always perform quantum experiment with probability 1. So in this, in this world, people can, it's kind of, might be a lot of things in this kind of universe. And there is no Born rule whatsoever. And I still think that unitary evolution, Hamiltonian and whatever, it's quantum mechanics, it's a quantum world. It's a quantum world. Without Born, where we do not need a Born rule, so there is no essence. And so, what you will say about your QBism will not be applicable, it will not be able to describe it because the Born rule is not there completely.
So my first response is, QBism is such a different worldview from what you expressed that it is difficult for either of us to speak to each other. For instance, you say you can have a world with unitary evolution and never a measurement. And I would respond to that by saying QBism envisions a world in which there is only measurement. Unitarity is no different than making a quantum state assignment. It's cut from the same cloth. In fact, currently, Schock and I and my former student, John de Broda, are writing a paper with the title, if I can recall it correctly, Quantum Dynamics is When Nothing Happens for Me. An analysis, a QBist analysis of unitarity and decoherence. So the vision here is that the world is not evolving unitarily because, for instance, without us, there are no wave functions. So there would be no wave function of the universe. There would be nothing to evolve unitarily. It's just a completely different worldview. And it just doesn't fit the same terms. Your unitary evolutions are actual states of the world, of how the world is evolving. QBism would say, no, the world are all the set of experiences. Now, one would like to ontologize that and not reference, or at least some of us would like to ontologize that, and not always have to make reference to particular agents in making such a statement. But it's a world in which unitarity is not something real. So that would be my response as best I can do it.
I don't.
You don't understand it. You're going to say you don't understand it. But on the other hand, I would bet you've never read a QBist paper to try to understand it.
Wait. I don't want to know psi exists, not exist. The story is this is the world of our experience. Forget about physics. But there is a physics, there are laboratories. We go to laboratories and perform experiments. In this experiment, frequently we do that there are different outcomes. But let's assume a world in which we are careful. We are forbidden, let's say Soviet Union, everyone which will perform quantum experiment with possible different outcomes will be killed. So no one does it. And 200 years ago, there were no quantum experiments, so there is no clear reason that there was a split, that the probability was relevant. The Born rule is only when we perform quantum experiments. But now, imagine a world in which in all experiments it's arranged in such a way the probability is 1. No different probability. It's so, the Born rule is if it's psi square or whatever, alpha square. But now it's always, we have only one outcome. So, can you imagine such a thing? It doesn't contradict any, in real life we don't do this, but we might do this. We might go and never put single photon experiment in a place where we don't have a single photon source to go in. This is allowed, but it's not allowed to put a superposition in a single photon experiment, because then we can get click or not click. We will never do it. All experiments have definite outcome. They arrange like this. Use our formalism, whatever. Consider this wave function as a tool, like shut up and calculate. Calculate such a way that no experiment will have possible different outcome. Of course, it's very Gedanken, but it's not clear if it's completely impossible. Maybe it's possible. Can you consider this Gedanken story? We have a wave function, meaning, not meaning. I don't try to go into when we have big disagreement. We have agreement on what we see around. We have our experiences, and you are physicist, and so physicist, I go to laboratory to perform experiment. Let's say I will never do experiment in which I have different outcomes. It's always I can calculate in before and put the detector in the right angle, so there is only one outcome. So it's still, I don't have life. I can live in such a universe. I will see the same trees, and only I have to be careful with quantum experiment. And I think my theory helps me to tell what will happen. You say your theory is a Born rule. The Born rule is not relevant here. So what will I do?
I'm trying to.
Yeah.
But
Okay.
I can see the basic issue is that I started by saying we are born into a world of uncertainty. And then we develop decision theory. And that the calculus of quantum mechanics is a species of decision theory. That's what it has always been about. The many worlds picture attempts to extract an ontology consistent with that makes things like wave functions, the wave function of the universe, and unitary evolution ontic elements. But I never allow that move. So I don't allow it because it makes quantum theory unintelligible then. Simple as that.
Okay, we have to switch to another question. Alexei.
Yes. So thank you, Chris. I think you're fundamentally missing the target. So the mystery of quantum theory, both historically and conceptually. Historically, starting with Solvay and whatever, comes from the fact that there is abstract mathematics, which is confronting empirical reality, and people all the way back in 27 and they were saying, well, how come you have this matrices, complex numbers, and all that stuff about reality, these historic debates. So this question has evolved into many different shapes, and one of those shapes is the question of complex numbers, which you are addressing on the mathematical side of what you presented you're addressing through increasing the dimension, doubling going to the square of that dimension and saying, yeah, we can deal with real numbers in that case. We can replace our matrices by real number matrices in the squared dimension. Sure. But that's not the target. The target here is why is there a continuous number field in these high dimensional representations? So you can say it's a dimension 2 Hilbert space or dimension 4. You can, if you have quaternions, you can probably go to a lower dimension. So the real mystery here is mathematical, and the answer to that cannot be I want to remove complex numbers by going to a higher dimensional space with real numbers, because that, sure, that sounds mathematically plausible, not trivial, I agree in some dimensions, but plausible. So from the point of view of mathematical foundations of quantum theory, the two mysteries are continuity and correlations, and we'll leave aside the correlations. It's unclear why the subject born unto this world will even choose real numbers or complex numbers, a continuous number field, rather than making these bets with rationals or something else. So it sounds like you're already admitting this big mystery as a given, and then you're saying, well, can we write the Born rule in a more cunning way so that we can get rid of complex numbers? Well, yes, we can, through the symmetric informational complete structure. But to me, you're missing the target, which is the actual mystery of this story. Why, in the first place, is there a continuous number field? And whether it's complex or real is not such a big deal.
There are layers. There are layers of work to be done. And I'm just a worker bee working on the layer that is the most accessible to me now. I think your point is well taken. But I wouldn't want to approach it without some solid guidance at a lower level, smaller mysteries. And that's where I am now. So, for instance, Savage, in his book for developing decision theory, if he wanted to get some clean theorems, then he had to have a way of well ordering the various preferences that one might have. So he took a basic framework of a problem that you're interested in, and then he added extra events, so that he ended up with a continuum of events. And then that would allow him to prove some theorems. Was it desirable to do that? Probably not. But then it just became too unwieldy of a theory, and he wasn't ready for it yet. So he ended up with probabilities being real number valued rather than rational valued, for instance. That's an addition that maybe.
There is always some kind of.
So my only response is I'm not ready. I like to stay close to the ground, actually. Despite I think Lev thinks I'm not staying close to the ground, but I think that to the extent that I want to ontologize, I want it to be a little step, and not. I use various metaphors for insulting many worlds. One is grasping in the dark for an ontology. Another metaphor is pissing in the wind for your ontology. It's just not constrained enough, it seems to me. Whereas I think QBism is slowly building a constrained, constructive program for going in some direction. The phenomenologists among us tell us it's going in the phenomenological direction. Some people say, oh, you're going in the Kantian direction. I don't think so. But yeah, I don't quite know what direction it's going, but it's little steps, little baby steps.
No, but it is revealing. One last remark. It was revealing when you had a list of these different philosophers and you said, well, I'm comfortable with any of these 6 readings or 7 readings.
Oh, I said there are ideas to be harvested.
Well, yeah,
I didn't say it that way, but I would say there are ideas to be harvested. I think they're all different.
Right, and I think a phenomenological reading now, if you want a philosophy comment before we continue, a phenomenological reading would go way farther. I think you're too much of a realist for a phenomenologist. I don't know what Michel thinks or thinks about it, but definitely this whole story that somehow they make bets on objects or systems that are there, there is too much furniture around for a phenomenologist. Everything needs to go into a phenomenologist approach, not just probabilities. So in that sense, there is definitely, I would say, a long road to be taken to make everything consistently phenomenological without the realist furniture around these 2 guys who are making bets.
Could be, yeah. I think that's a real possibility. I'm willing to harvest. If I can harvest anything from these guys, I will, and turn it to my purposes. And if I can't,
Yeah.
Now my colleague Rudiger Schock is closer to saying, oh yes, there's very good stuff to harvest from here, and so is Jacques Pinard. But I'm not inflexible. If I see that there's something to be learned, I will do my best to learn it. And if something feels like it's on the wrong path to me, then I'll reject it.
Michel?
Oh, should I go? I should go over there so you're not turn your head. I see. Did it?
You see?
I see part of the bump.
Yeah.
Wow.
Okay. So, since I am invited to adduce the phenomenological point of view, I would say phenomenology is very simple. You turn everything back to lived experience and nothing else. So there are 2 questions for a phenomenologist. One is the order of experiences such that you can accept that these experiences are appearances of something which is independent from us, from the subject. So if the order of experiences is such that you can disentangle, so to speak, the subject and the object, then you can speak as if there were objects out there. One. Second point, in classical physics you can do that usually. And this has been shown by Kant, especially in his critique of purism. In quantum physics you cannot. And you cannot because the order of experiences in this case is constrained by a structure of probability that doesn't fit the idea that there is a complete separation between the subject and object. There is participation. There is interaction. You cannot eliminate that from the structure of our experience. But then, the second point for a phenomenologist, if it is indeed impossible to completely, separate the 2 sides, the question is, now that you cannot separate 2 sides, one side subject and one side object, is it the case that in your experience there are the marks of what you call participation and what Renaud Barbaras calls belonging, namely the mark of the fact that experience is not the experience of a solus ipse, it's not the experience of one who is completely alone in the world, but it's the experience of someone who is partaking of something that is broader than this particular subject, and yet not completely different from experience itself. So you see, there are two steps, and as you noticed, my tendency was to go to the second step under your pressure, because your pressure was very strong.
I've never pressured you.
No, but the pressure is, sound thought, and I think that.
And so, what is the second again?
The second is, if you cannot separate, if your experience, the order of your experiences is not such that you can believe that this is the experience about something completely independent of you, then is there a sign in your experience that your experience is overflowed by a part of experience which is not your personal experience?
Yes.
Okay? And this is exactly the sense.
So Barbara's
belonging or Merleau-Ponty's flesh. Merleau-Ponty's flesh is exactly that. There is something that goes beyond my personal standpoint, but this beyond is not completely different from lived experience of being embodied. It's just a broadening of our embodiment, and this is why he speaks of the flesh of the world.
This can be the dimension.
So I want to say two things. One is more basic, but just first to respond a little bit to that. I've come to think of the formal structure of quantum theory, everything that we've talked about today, as something that is rather high level. We have gained it because of our involvement in larger communities. But then we use it individually. But it still carries the hint of larger things. I think that connects a little bit to what you're saying. But even if it doesn't, here's a different idea. And this is, when I hear phenomenologists like, who is our friend, Bob Crease, use language like phenomenologists always want to stick with the given or rely solely on the given. I think of this experiment. I'm not going to drop them, but I put them at the same level and they fall. And it is my experience that they hit at the same time. It was the experience of Galileo that they hit at the same time. This is the given. At least I think, is we each have this given. And it was probably noticed in Platonic times, but no one ever said it. Surely people have noticed that two rocks hit the ground at the same time. So this is in the given. And then Einstein saw this same experiment. Something popped out of his head that wasn't in that. And that was the principle of equivalence. And so I have a hard time thinking that everything can be traced back to previous experience or the full set of previous experiences. Sometimes there are creative leaps in which something new comes into the world that is, in a sense, a new experience, but it doesn't flow out of all of the previous
Letter
things.
to Solovin. Einstein's letter to Solovin says exactly that.
Okay. So this is part of my reluctance with the phenomenological program. Maybe I can be dissuaded of it, but it's just a very simple point. And then once Einstein saw the principle of equivalence, did the head explode? His head exploded. He said it was his happiest moment in his life when he appreciated this. Then it just changed everything. It gave him a program to work toward. And I think that Einstein wanted to turn that observation into an ontological statement. That space-time is a curved manifold. And then he was able to develop things by playing the game. Somehow someone has to choose the right words here. Einstein, I'm quite sure, didn't just say, oh, space-time is a manifold and that's that. I've solved it. He saw it as a new tool for thought. And the new tool for thought was hypothesizing, making up, running with the story. Let me just use different ways of it, trying to express it. That by running with the story that reality is this, reality is X, then he could make progress. Because, in fact, the very first step of it wasn't given in experience. Not in any obvious way, it doesn't seem to me. The first step was the creative explosion. There's something behind this. And it's a very simple thing. It's the reason they hit the floor at the same time is because the floor is moving up. Now it makes sense. Now there's a conceptual framework.
Yes, just a point. A phenomenologist doesn't deny that. A phenomenologist would just go much below this level to ask very elementary questions. For instance, is the order of experiment results such that you can detach something from the act of making an experiment? Depending of whether you have commutativity or non-commutativity between two kinds of incompatible tests, either you can detach something from the very act of making an experiment, or you can't. This is very elementary, and I think this going down to elementarity is typical of what some scientists do during scientific revolutions. For instance, Heisenberg went back to the observables. Einstein said, I don't want to speak in abstracto about space and time, but I want to speak about ways to check simultaneity.
Yeah.
And this is typically a gesture of phenomenologists, going down.
I agree, and I see the value in that.
Yeah.
But I don't know that it exhausts.
Yeah, exactly. It doesn't.
That's the issue,
right.
is whether that exhausts.
This is right.
And similarly with the first person element in QBism.
Yeah.
I proposed this idea of participatory realism, I called it, from John Wheeler's Participatory Universe. But it's the recognition that the first person cannot be... So many worlds, I would say, is the beautiful embodiment of the idea that the first person is purely contained in the third person. It's all there somehow in the third person picture. And this says, no, there are genuinely separate worlds, not just branches. And that's part of the story. But I'm not sure that exhausts everything.
No,
I'm sorry. We have to
just
take
the
away
last
from
remark. The last remark is, you are absolutely right. It doesn't exhaust everything. Yet, for the sake of conceptual coherence, it is worth trying to embed all your remarkable results within the framework of lived experience. And see if this is still something that can be done.
And I cannot disagree with that either. It's a methodology.
Yes.
And I suppose at the moment I haven't so committed myself singularly to that methodology. Sometimes I do and sometimes I don't. I mean, I often explain to people who want to convince me of their view, life is short and I only have time to do one thing. And I'm going to doggedly follow this path that I call QBism, and I welcome you to try your own path.
And we are thankful for that.
Okay, so I'm sorry, we have to stop now. Thank you guys.
Thank you.
And that's the discussion to continue, of course.